Okay, so I need to talk about another block, which is called the demultiplexer. So I need to talk about a different combinational circuit. So it's called the demultiplexer or a DMUX. It's a combinational circuit that has one input I. It has an n-bit select input. So notice that here S consists of n bits. This is used for selection. And it has a maximum of 2 to the power n outputs. So now when S equal to 0, now because S consists of n bits, okay, and you have 2 to the power n possible combinations, possible values for S. Okay, so you will have 2 to the power n binary values for S. So when S equal to 0, you would like to direct the input I to the output D0. When I is equal to 1, you would like to direct the input I to D1. When S, so this is when S equal to 1. When S is equal to 2, you would like to direct the input I to D2, and so on. So really the demultiplexer, what it is doing, it is directing the data input to one of the outputs according to the select input S. That's the demultiplexer. So the demultiplexer is the inverse operation of a multiplexer. That's what it does. Okay. I have examples here about demultiplexers. So the simplest demultiplexer, it will be 1 to 2 demultiplexer. Notice that there is only one select input. We have the input I here. We have one select input. So if S is equal to 0, we can express this with an if-else statement. So if S is equal to 0 here, then D0 is equal to I, and D1 equal to 0. Else, it means that S is equal to 1, then D1 is equal to I, and D0 equal to 0. So if S equal to 0, this input is directed to output D0. If S is equal to 1, then we direct it to output 1. That's what the demultiplexer does. You can have a 1 to 4 multiplexer, so it has 4 outputs, so therefore it has 2 select inputs, S1, S0, because we have 4 outputs. So we can have 0, 0 for selection, then D0 is equal to I. When you have 0, 1, then D1 is equal to I. When you have 1, 0, then D2 is equal to I. And when you have 1, 1, then you have D3 equal to I. Notice that all the remaining outputs are zeros. All of them are zeros, except for one. Only one of the outputs will be equal to the input I, and all the remaining outputs are zeros. Now you can easily obtain the logic expressions, okay, for a demultiplexer. It's not be that difficult at all. We can easily obtain these expressions, the output expressions. So for example, if I have a 1 to 2 demultiplexer, so we only have 2 outputs, D0 and D1. So D0 will be equal to I when S equal to 0. So therefore, we can write it like this. D0 is equal to I and S prime. So when S equal to 0, you get I. And D1 will be I and S. So it means that when S is equal to 1, you get D1 is equal to the input I. Okay? When you have a 1 to 4 demultiplexer, we have 4 outputs. So each output can be written with an expression, okay? Very simple expressions. So when D0, so D0 is equal to I, when you have S1, S0 are both equal to 0 and 0. So it is I and S1 prime and S0 prime. So because when S1, S0 are 0, 0, you get D0 is equal to I. Now, for D1, it will be I and S1 prime and S0. Because when S1, S0 equal to 0, 1, you get D1 is equal to I. And so on. Notice that D3 here is equal to I and S1 and S0, because when you have S1, S0 is equal to 1 and 1, you get D3 is equal to I. So these are the expressions. Okay, these are the expressions for the outputs of the demultiplexer. Right, let me ask you this question. Okay, have we seen something similar before, similar to a demultiplexer? And so far from my last lecture, I talked about decoders, encoders, priority encoders, multiplexers. Have we seen something similar to a demultiplexer?
Encoder?
I don't know.
Encoder?
Decoder, not the encoder.
Decoder. So how is the decoder similar to a demultiplexer? You are right. Okay, the decoder, okay, has 2 to the power n outputs. Remember the decoder? It had 2 to the power n outputs. So it is similar to a demultiplexer. It has 2 to the power n outputs.
Only one of the outputs is 1?
So only one of the outputs is equal to 1 and the other ones will be zeros.
Yes.
So yes, Ahmed, can you tell me more about this? Can we make the demultiplexer similar or equivalent to a decoder? Are they equivalent? Are they identical circuits?
I'm not sure. I think we can make a demultiplexer from a decoder.
How?
I'm not sure. I'll have to think about it.
Okay.
But it seems as if it's possible.
Yeah. In fact, we can. In fact, we can. Yes.
Doctor?
Now, yes, go ahead.
What if we replace I by 1?
Yes. If we replace I with 1, yes. صحيح. Any other idea? Remember the decoder that has an enable input? The decoder that has an enable input. So we had decoders with enable input. Remember that? I talked about it in a previous lecture. So in fact, the demultiplexer is equivalent to a decoder with enable input. Let me give you this example. This is a demultiplexer. Notice that the input here is I. My select inputs here are S1, S0. And it has 4 outputs, D0, D1, D2, D3. One of the outputs is equal to I, and all the remaining outputs are zeros. That's in the case of a demultiplexer. Now, I can use a 2 to 4 decoder. I'm going to use here my inputs S1, S0 here. I'm going to decode here my inputs S1, S0. So I'm going to connect them to A1 and A0. These are the inputs of the decoder. And I'm going to use the input I to enable the decoder. I'm going to use the input I to enable the decoder. So if I is equal to 1, then this decoder will be enabled. And therefore, one of the outputs will be equal to 1 according to S1, S0, right? And that's exactly what you will get from the output of the demultiplexer. Only one of the outputs will be equal to 1, and all the other ones will be zeros. So basically, we're getting exactly the same thing. Right. Now that's if I equal to 1. What if I equal to 0? If I equal to 0 here, then basically you get all the outputs are zeros, okay, regardless of S1 and S0. You got all of them. So one of them will be I, but I equal to 0. So therefore, all the outputs are zeros. And this is the same thing like in the case of a 2 to 4 decoder. You get all the outputs are zeros if it's not enabled. So we can think here about a decoder as directing the enable signal to one of the outputs. And therefore, in general, you can take any demultiplexer with n select inputs, and you have 2 to the power n outputs, and you can implement it using an n to 2 to the power n decoder with enable input. So it is equivalent. We don't really need a demultiplexer. Why? Because we can always implement the demultiplexer using a decoder with enable input. So they are identical. So the demultiplexer and the decoder with enable input, they perform exactly the same function. They provide exactly the same output. So for this reason, we don't really need demultiplexers. So the demultiplexers is equivalent to a decoder with enable, and therefore you can just use the decoder with enable as a demultiplexer. Okay? We just actually have to change the inputs in a certain way, and basically they are equivalent. So one is equivalent to the other, so we don't really get actually any new functionality. So the outputs are identical. Fine. Is this clear? Do you have any question about this? So really, we did not really get anything new here, okay, the demultiplexer, because it is a decoder with enable. So just use the decoder as a demultiplexer, and that's it. Okay. Fine. Now, let me show you some design examples. Before I move on to design examples, do you have any question about all the topics that we have seen? So we have seen actually many different blocks: decoders, decoders with enable inputs, encoders, priority encoders, multiplexers, demultiplexers turn out to be decoders with enable inputs. Okay. Now we are going to have to design at a higher level. Yani I'm not going to use now the Carnot map and gates at the gate level. No, we're not going to do that. We're going to actually use the blocks that we have seen in this lecture, and we are going to design using these blocks. Okay, so we can design larger combinational circuits this way. We can also use arithmetic blocks like adders, comparators, okay, and also in our design. So we have already studied these under arithmetic circuits. So let us actually take a look at some of these design examples. Let us design a 2x2 crossbar switch. So what is a crossbar switch? Crossbar switch is a combinational circuit. It has two inputs, A and B. These are the inputs here. Now, A consists of M bits and B consists of M bits. You can decide on M, okay? It can be any number of bits. And it has a select input. It is just a 1-bit selection. And it has two outputs, X and Y. X and Y consist of M bits. We can describe the 2x2 crossbar switch with an if statement. If S is equal to 0, then X becomes A. So A here is passed to the output X, and Y becomes B. So that's what it does. Okay, that's if S equal to 0. So if S equal to 0, we select X becomes A and Y becomes B. If S is equal to 1, then we reverse them. Then X becomes B and Y becomes A. So notice that here that X becomes B and Y becomes A. So that's basically the crossbar switch. So the question is, how do I implement this 2x2 crossbar switch? Any idea? Well, it is actually shown here that using multiplexers. I don't really have to tell you using multiplexers. I might just actually ask you to implement the 2x2 crossbar switch, but you have to figure out, okay, that how to implement this multiplexer using the blocks that we have seen so far. So if I would like to use now the blocks or the components that we have, if I have now a library of components, and I would like now to use them to implement now a crossbar switch, which one do I select? Okay, so I'm going to actually use multiplexers, okay? But how? How many multiplexers do I need? Students?
2M.
Well, yes, but we can think about them as M-bit. So we need actually how? Okay, so these multiplexers are what? What's the size? So what are the size of these multiplexers? Okay, how many inputs? How many out? How many inputs do we have?
2 by 1 multiplexers.
Exactly, 2 by 1 multiplexers. Okay, so we agree that we have 2 by 1 multiplexers, and of course, each multiplexer will have m inputs. So we can think about them as 2 multiplied by m, okay, because we have actually m inputs. But we are going to draw them as just 2 multiplexers. So we need one multiplexer for x, and we need a second multiplexer for y. But these are m-bit multiplexers. Okay, so their inputs are bit vectors. Yes, so therefore we are going to draw here 2 multiplexers, one for x and one for y. Now notice that I'm going to connect A and B to both inputs of these 2 multiplexers. So notice that here A is connected to input 0 of the first multiplexer, while A is connected to input 1 of the second multiplexer. And B is connected to input 1 of the first multiplexer while it's connected to input 0 of the second multiplexer. So the wiring is very, very important. How you do the wiring, how you connect the inputs to these multiplexers. So now when S here, S is used for selection. So when S is equal to 0, then X becomes A, and Y becomes B. That's when S is equal to 0. Okay. On the other hand, if S is equal to 1, then X becomes B and Y becomes A. So we have basically switched the outputs. So that's what the crossbar switch does. And it can be implemented using 2 input multiplexers. And we have used 2 of them, but of course, each one of these is basically having m-bit inputs. Okay, so the inputs here are m-bits, so these are actually bit vectors. Right, so this is the implementation of a 2 by 2 crossbar switch. Crossbar switches are very useful. Okay, people actually use them a lot in designs. For example, people use them when they are designing networks on chip. They use them in switches, okay, in routers, okay, because they can switch or route the data. So this is the importance of the crossbar switch. You can also have additional functionality, which is not really shown here in this slide. Yani, for example, rather than using actually 1 selection bit, I can use 2 selection bits. So we can have 0, 0, 0, 1. We have 1, 0, and 1, 1. I can use additional selection. For example, I can have X and Y both equal to A. I can broadcast A to both outputs X and Y, and I can broadcast B to both outputs X and Y. So I can say that X and Y are both equal to A, and I can say that X and Y are both equal to B. So I can actually have even more possible outputs, okay, out of this crossbar switch. So we can even add more functionality to this crossbar switch. So this is just an example of a small 2 by 2 crossbar switch, which is implemented using 2 input multiplexers. In fact, we can also have large crossbar switches like 4 by 4 crossbar switches, 8 by 8 crossbar switches. These are also possible. They will be, of course, more complex to implement. Right. Let us design a circuit that does sorting. Suppose I would like to sort 2 unsigned integers. Okay, so we would like to design. So there are actually circuits that actually do sorting. You can actually sort numbers with a circuit. Okay, not just with a program, with software. You can design hardware to do sorting. So my inputs here are A and B. These are 2 m-bit unsigned integers. And the outputs here are X and Y. X is the minimum and Y is the maximum. So I would like to compute the minimum of A and B, and I would like to compute the maximum of A and B. So let us design this circuit. So let me ask you this question. What do you need, okay, to design and draw this circuit? What are the components that you need inside the circuit? Students? You might actually easily get something like this. Yani. Yes, Hammam, fadal.
Multiplexers and magnitude comparator.
Yes, why do I need a magnitude comparator?
So I can determine which is the minimum and maximum.
Yes, so that you can actually compare them. Exactly, exactly. For example, all what I need is just to know if X is less than Y or not. That's it, right? And I need multiplexers to what? For what? So I need a yes, go ahead.
To assign the suitable variable A or B to the max or the min.
Exactly, exactly. So we have two outputs here, so we have to select. So we have to select actually between A and B. Okay, so which one is the minimum and which one is the maximum? Right. So we are going to use a magnitude comparator to compare A with B. So that's the need for the magnitude comparator. And we are going to use a 2x2 crossbar switch that we have seen in the previous slide. And this crossbar switch can be implemented using two input multiplexers. So again, we use multiplexers, okay, for selecting the minimum and the maximum. Right, so here we go. So this is the m-bit magnitude comparator. So the inputs here are A and B. That consists of m bits. And the outputs, we have A less than B, A equal to B, and A greater than B. I don't really need these outputs here. It's enough to use one of them, and A less than B, because if I know that A is less than B is true, is 1, then I know that A is the minimum, and B will be the maximum. And otherwise, we can just reverse them. So all what I care about is just I only need actually one output of this magnitude comparator, which is A less than B. So if it is 1, then we select X is equal to A, and we select Y is equal to B. And if it is 0, and if it is A is not less than B, and it means that it is greater than or equal, then we reverse them. And we use this actually to select that X becomes B and Y becomes A. So we just reverse the output, we change the output. So for this reason, we need two multiplexers. So we take this output here and we connect it to the S input for selection. So the output of the magnitude comparator is used to select what should be X and what should be Y. So if this S here is equal to 1, that's an indication that A is less than B. So notice that input A here is connected to input 1. This is very important how you connect, okay, the inputs of these multiplexers. You have to indicate, you have to show this very clearly in your solution. So when you are drawing a solution in a quiz or in an exam, it's very important that you show that the inputs are connected. So you have to label the inputs of the multiplexer so that you make it very clear that if S is equal to 1, you are going to select input A, and A becomes the minimum. Okay, and so that's the A is the minimum. Notice that here B will also be connected to input 1. That's actually the input B is connected to input 1 because B now becomes the Y, becomes the maximum. Now that's when S is equal to 1. On the other hand, if S is equal to 0, okay, notice that B, if A is not less than B, and B is the minimum. So we could now we select B is connected to input 0, and A here will be connected. So now B becomes the minimum and A becomes the maximum. So this is basically how we can implement, okay, the how we can design a circuit that does the sorting of two unsigned integers. So we use a magnitude comparator to compare A with B. And we took the output here, which is the less than output, and we use it actually for selecting what will be the minimum and what will be the maximum. So we use here a 2x2 crossbar switch. This is basically my crossbar switch here. And we have implemented already the crossbar switch in the previous slide using two input multiplexers. Okay. Right. Let me move on. Okay, here's another design example. I would like to design a circuit that does arithmetic and logic operations. So this is called an arithmetic and logic unit, or ALU. So A here stands for arithmetic, L stands for logic. So this is an arithmetic and logic unit. Now this arithmetic and logic unit, it exists today in any computer system. Yani if you look inside the CPU, inside your computer, you will find even hundreds of these ALUs inside your CPU. So there are many ALUs inside your CPU. Now, a simple ALU is shown here in this slide. It has two data inputs here, A and B. So A and B are my data inputs, each one consisting of n bits. You can decide on n. Yani for example, you can have 8-bit, 16-bit, 32-bit, or even 64-bit ALUs, depending, of course, on n, the number of bits in A and the number of bits in B. We also have here a function, f. It only consists of 3 bits. Because we only have 3 bits for the function, we can have 8 possible functions. So f here can be 0, 0, 0 up to 1, 1, 1. So we have 8 functions. We can use some functions for arithmetic. We can use some functions for logic. So for example, if f is equal to 0, 0, 0, then I would like to do addition. So my result here is an output. R here is my output. And R will be A plus B. So I would like to do addition. So if the function equal to 0, 0, 0, then we add, and the result will be the addition. So we use the function here, f, to control the ALU, okay, to specify what's the function or the operation that should be done by the ALU. If I have the 0, 0, 1, according to this table, I would like to add a plus 1. So it will be A plus B plus 1. If I have 0, 1, 0, I would like to do subtraction minus 1. It will be A minus B minus 1. And if it is 0, 1, 1, I would like to subtract A minus B. Now, if I have 1, 0, 0, I would like to end. So this is A and B. Now, this is bitwise ending. Yani bit 0 with bit 0, bit 1 with bit 1. So basically, the bits are ended bitwise. We can OR, we can say NOR, not OR, and we say XOR. So we have here 4 logic functions, okay, which are defined in this table. So in total, we have 8, 4 arithmetic and 4 logic. So now what we would like to do is that we would like to design this ALU that has 8 functions. And notice that's going to produce a result here, and is going to produce also a carry and overflow. So V here indicates overflow. It can detect overflow. In the case of overflow, the V out will be equal to 1. Right. I'm not going to do it now because I'm running out of time, but let me ask you this last question. If I would like to design this ALU, how many adders do I need inside this ALU? How many adders do I need? Students, if I give you this question, okay, in an assignment or in a quiz, how many adders do you need to implement this ALU? I need a quick answer. خلاص, we're running out of time. It's time now.
4.
Someone? Yes, Ahmed, تفضل.
4 bits adder.
Do we need actually 4 adders?
1.
1 will be enough. We can use the same adder to do addition and subtraction. Okay, we'll see this inshallah next time. So in order to subtract, you can add to the 2's complement. So why do we need actually 4 adders? I can use 1 adder. Now to add plus 1 here, I can use C0 as equal to 1. I can use it as a carry, input carry. And to say here actually minus B minus 1, that can also be implemented very easily. So therefore, we don't need actually to have 4 adders. It's only 1 adder, which is sufficient. Right. So In the case of R is equal to A minus B. In the case of subtraction, it will be A plus the 2's complement of B. So I can write it as A plus minus, so this is not B plus 1. Okay, so that's A plus the 2's complement of B. It's A plus not B plus 1. Okay, not B here is the 1's complement of B. Now, in the case of A minus B minus 1, we cannot use minus 1 as an input carry. The input carry can be either 0 or 1. It cannot be negative 1. But what we can do is that we can say that this is A plus the 2's complement of B minus 1. So plus 1 minus 1 will give you A. So this will give me A plus not B. That's it. So it's A plus the 1's complement of B. So we can use the same adder to do all of these 4 functions. We need also 4 more functions here, okay, for AND, OR, NOR, and XOR. This is here the AND operator in Verilog. This is OR. This is not OR, which is NOR, and this is XOR, okay? So these are the operators which are defined in Verilog. So what we need actually only one adder to do the arithmetic. But what else do I need for the logic functions? In addition to the adder, what else do I need?
One gate for each operation.
So yeah, but is it only one gate? Yani, for example, do I need one AND gate? Well, we need n AND gates because we have A and B are n-bit inputs. So we need AND gates. Okay, we need OR gates. We need to implement the NOR, we need inverters, right? So not OR will be NOR. And we need XOR gates. Yes, so we need all of these gates. What else do I need? But in addition to gates, okay, to implement the AND, the OR, the XOR, and the NOR, what else do I need?
Multiplexer.
Exactly. I need multiplexers. Why do I need multiplexers?
To select the desired function.
Yes, I would like to select what should be my result according to the function. So that's exactly why we need multiplexers. So now we can design a simple ALU, okay, by thinking what are the components that I need inside my ALU. I'm going to use here an n-bit adder, only one adder that is going to add n bits. So A here consists of n bits, B consists of n bits. But in the case of subtraction, I need to take the complement of B. So in order to take the complement of B, I can use the XOR gate. In fact, I need n XOR gates to XOR B with F1. Now notice that in this table here, when F1 is equal to 1, here F1 is equal to 1, this is F1, then we would like to do subtraction. So when we would like to do subtraction, I need the to invert B, I need to take here not B. Okay, not B. So not B is the 1's complement of B. We can use the XOR gate. So when you XOR with 1, if this is equal to 1, you get not B. The output of the XOR gates will be not B. So we are inverting every bit of B. And when F1 is equal to 0, we get B. So when you XOR with 0, you get B. When you XOR with 1, you get not B. So therefore, we can use the same n-bit adder to add A plus B. And we can also use it to add A plus the not B, the 1's complement of B. So that's based on F1. So notice that here when F1 equal to 0, we add. In the case when F1 is equal to 1, we subtract. So we add to the 1's complement of B plus 1. Now the plus 1 here, notice that here I have plus 1, here I have plus 1. So this is based on this F0. So notice that here I have F0 equal to 1. This is F0 equal to 1. So I can use here, I can connect F0 to C0. So if F0 equal to 1, we are adding +1. So if I would like to say A minus B, it will be A plus not B plus 1. So the F0 here will be equal to 1, and this will be A plus the 2's complement of B, and this will calculate A minus B. The same thing, for example, when I would like to calculate here R is equal to A plus B plus 1. So notice that here, this one here comes from F1. So I can just connect the function bit here, F1, to C0 for adding +1. It's a small trick which is needed to add the +1, okay? In the case of A minus B minus 1, okay, this is when F equal to 0, 1, 0 here, then I just need to add A plus not B. So C0 will be equal to 0. So notice that here that F0 equal to 0, here F0 equal to 0. So the C0 will be equal to F0 equal to 0 in that case. And that one I would like to calculate A minus B minus 1 or A plus B. In the case of the carry here, we have the carry, the output carry. This is C here is C sub n. That will be the final output carry. And in the case of overflow, I need Cn and Cn minus 1. I need the last two carries and an XOR gate to produce the overflow output. So V here means overflow, and we need to XOR the last two carries to produce overflow. So this will indicate overflow in the case of addition or subtraction. Right. So this is for the first four functions that exist in the first part of this. Let me just erase all the ink. So we have implemented all of these four functions. These are the arithmetic functions. In addition, I need to implement the second part of this table. These are the logic functions. So I need here n AND gates. So this is called bitwise ending. So I'm going to end every bit of A with every bit of B. These are OR gates, n of them, n OR gates. These are n XOR gates. I'm using here also inverters to obtain not OR. This is NOR. So this is basically it. Okay, so we can actually have AND, we can have OR, we can have NOR and XOR. And we need here the F1 and F0 as my select inputs to select, okay, what should be the result of this ALU. So notice that here F1 and F0 as indicated here in this table. So 0, 0, we select AND, 0, 1, it is OR, 1, 0 is NOR, and 1, 1 is XOR. So I'm using F1 and F0 to select my result. Okay. That's why we selected here using F1 and F0 as my select inputs. So here we have the output of the adder. Here I have the output of this multiplexer. We need actually F2 for my final selection. Okay, to select whether the result is the output of the adder or my result is the output of a logic gate. So this is done using F2. So in this table, if you look here at F2 here equal to 0, that indicates the output of the adder. Here F2 equal to 1, it means that we would like to select the output of a logic gate. So it will be a logic function. So we use F2 for the final multiplexer. So I'm using more than one multiplexer here. I'm using this multiplexer here to select the final result. So the final result will consist of n bits, plus we have 2 additional bits for overflow and for carry. So this is how we can design a simple ALU. Okay, so any question about this example? So you can see that we have used different blocks here. We have a block for the adder. We have a block here for the multiplexer. We have, in fact, more than one multiplexer. We have a 4x1 multiplexer, a 2x1 multiplexer. We use additional gates, okay, to implement the logic functions, and we have produced an ALU.